Welcome to Lesson 4E, Heat Equation in Primary Variables. In this lesson, we'll review Fourier's law of heat conduction, which will allow us to transform the differential heat equation into a more useful form containing primary variables, and then we'll simplify it for several cases. Here's the heat equation that we derived in a previous lesson. I'll call it equation 1. In order for it to be useful for solving fluid mechanics problems, we have to put terms such as E, Q, and phi into primary variables, and I should add, and fluid properties. Primary variables for a general compressible flow problem are rho, ui, p, and t, and the properties are viscosity mu, coefficient of thermal conductivity k, second coefficient of viscosity lambda, and whatever other properties we may need. Let's deal with this heat flux term first. We use Fourier's law of conduction, which we can write as Qi equal minus K del T del Xi, where K is the coefficient of thermal conductivity, and Fourier's law applies at a surface. The term in the heat equation has the derivative of Qi, so we write del Qi del Xi equal del Xi of this right-hand side. The two negative signs cancel, so 1 becomes rho dE dt equal del Xi of K del T del Xi minus P del Ui del Xi plus phi. So we've partially achieved our goal. This term is now rewritten in terms of T, one of our primary variables. We still have to deal with E and phi. We're going to consider only Newtonian fluids, where we previously showed that phi is tau ij del ui del xj, which reduces to 2 mu capital Sij plus lambda del ui del xi del uj del xj. So we'll plug this grouping of terms in place of phi. We note that this is in terms of primary variables because Sij is the strain rate tensor, which is 1/2 del ui del xj plus del uj del xi. Everything here is now in terms of primary variables and fluid properties. Now the only thing left to work on is this internal energy term, which we'll have to consider for various types of fluids. We'll consider first the heat equation for an incompressible liquid. Note that this will be valid for liquids only. We'll treat gases next. The incompressible approximation is from continuity that del ui del xi equals 0. That will get rid of this term, the term containing lambda. We also typically assume that k is a constant, so it can come outside the derivative in this term. And then finally, for an incompressible liquid, dE dt equals C dt dt, where C is the specific heat of the liquid. I note to the side here that for an incompressible liquid, there is no distinction between Cp and Cv, Cp being the specific heat at constant pressure, and Cv being the specific heat at constant volume. In other words, C equals Cv equals Cp. We'll use Cp. Thus, the heat equation for an incompressible liquid becomes rho Cp dt dt equal K del squared T del xi plus 2 mu Sij. I'll call this equation 2, which is the heat equation for an incompressible liquid. We have accomplished our goal. All the variables here are now primary variables, where Sij can also be written in primary variables. I write it like this just to save space. If we expand Sij, we would get this form. Some of you may be tempted to use this equation for gases as well. Dude, I'm tempted by a lot of things, but not that, man. I am tempted to skip these lessons to go to the gym. I'm tempted to sleep through these lessons, Sonny. And I'm tempted to listen to music instead of paying attention. Okay, guys, I get the picture. I'm tempted to do what you said, sir. Thanks, Ned. Like I said, some of you may be tempted to use this equation for gases as well, but the only gases we'll consider here are ideal gases. So let's look at the heat equation for an ideal gas. Note that an ideal gas is by definition compressible. I'll write this statement. It is impossible to have both an ideal gas and an incompressible gas. at the same time, since an ideal gas is compressible. Note that some people call ideal gas a perfect gas. We write P equal rho RT, the ideal gas equation, and Cp and Cv are different. In fact, Cp equals Cv plus R, whereas for an incompressible fluid, like our incompressible liquid above, rho is approximated as constant, and as we said, Cp and Cv are the same. We also assume that these are constant. Comparing these two, they're incompatible. You may also recall from your thermo class, for an ideal gas, dH is Cp dt and dE is Cv dt, where H is specific enthalpy and E is specific internal energy. We'll use this one to plug into equation 1. So equation 1 becomes, if we let Cv be a constant, rho Cv dt equal del xi of k del t del xi minus p del ui del xi plus phi, where I left k inside the derivative since it may vary if the flow is compressible and if temperature varies considerably. You can show, which I like to say on some cold rainy night, that rho Cv dt plus p del ui del xi equal rho Cp dt minus dp dt. Notice that these three terms have material derivatives, and this is valid, of course, for an ideal gas. Why did I do this? Well, you can see that this term is the same as this term, so this equation becomes rho Cp dt equal dp dt plus del xi k del t del xi plus phi. This is now our heat equation for an ideal gas. Note that we can expand phi as before, but we have to include the lambda term since the ideal gas is compressible. I'll call this equation 3. Again, in terms of all primary variables, if we write out phi with the lambda term included, we get this expression, which as you can see is now our heat equation for an ideal gas in terms of only primary variables and fluid properties. We usually write it this way though, just for compactness. Finally, let's consider this ideal gas at very low speeds. In other words, consider an ideal gas at very low Mach number. In undergraduate class, we just say that this is nearly incompressible, but the gas is an ideal gas, and as I said, these two are incompatible or contradictory. If we use the incompressible form that we had derived for a liquid, which C do we use, Cp or Cv? For an ideal gas, Cp equals Cv plus R. No matter how slow the gas is moving. This applies even for a gas that is stationary. In other words, Cp is not equal to Cv, so our incompressible liquid heat equation is really not valid. So what do we do? The proper way to simplify our equation 3 is to let the Mach number, Ma, go to 0, and let change in temperature over temperature also go to 0. In other words, very small temperature changes. This leads to K being a constant, since T is approximately constant. We'll call these approximations the incompressible limit or the 0 Mach number limit for our ideal gas. After some algebra, equation 3 reduces to rho Cp dt equal K del squared T del xi plus phi. But in addition, phi also goes to 0. It has the same order of magnitude as the other terms that we neglected as Mach number goes to 0. So this equation, which I'll call equation 4, is the heat equation for an ideal gas in the so-called incompressible limit, which technically means Mach number goes to 0. This is the form we'll use when we're dealing with air at low speeds and small temperature changes. Finally, I typed up the various forms of the thermal or real energy equation, the integral form for a control volume, the general differential form, and what we call the heat equation for a Newtonian fluid with this viscous dissipation. And in this lesson, we rewrote this equation in terms of primary variables and properties by using the Newtonian fluid expression for phi, strain rate tensor, and Fourier's law of conduction. And we derived 3 simplifications, this form for an incompressible liquid, this form for an ideal gas at any speed, and this form for an ideal gas at very low Mach number. Thus we have 3 forms of the heat equation, We must be careful to use the appropriate one, depending on what kind of fluid and flow that we have. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.